On from where we left off last time. Last time we had finished computing the inverse Laplace transform of this expression right here, and the technique, right, was to do partial fraction decomposition. And once we did the partial fractions, we were able to invert the transform. So continuing on with these computational methods here for computing the transform, I wanted to do one more that's going to be a little bit different, and that is let's try to take the inverse Laplace transform of 2s plus 3 divided by s squared plus 2s plus 5. Okay, and the reason I want to look at this one is because in this case the denominator is not factorable. In fact, it's not reducible. And so, therefore, we have to do something a little bit different. And the thing that's different is we are going to complete the square in the denominator. And so the idea is that we're going to be using table entries 6 and 7, and just to write them up here real quick, that's e to the at sine of bt. Goes back and forth between b over s minus a squared plus b squared, and e to the at cosine of bt is s minus a over s minus a squared plus b squared. Okay, so this is, again, table entries number 6 and 7. Okay, and so you might see where we're going with that. And so let's just go ahead, and before I do any inversion, I'm just going to be doing some algebra. 2s plus 3 divided by s squared plus 2s plus 5. I'm going to complete the square in the denominator. And so I'll have s squared plus 2s plus 5 minus. Okay, and so what am I going to add and subtract there? Half the middle term squared, 1, half, and then if I add 1 there, I need to subtract 1 there. Okay, so that becomes 2s plus 3 divided by s plus 1 quantity squared plus 4. Okay, so now we see how this is going to work, I hope, if you look between these. Okay, so that's our table entries there. Okay, so let's take a look at this first one. I've got an s minus or an s plus 1 here, and so I need an s plus 1 in the numerator, and so I'm going to go ahead and write that in. I'll go ahead and keep the 2 there too. So I need let me go ahead and erase that, get it white again to be clear. So I'm going to go ahead and write 2 times s plus 1, and let's see what's left over now. That's actually 2s plus 2. I've got a 2s plus 3 over here. Right, so then that just leaves a plus 1. Okay, and so now I think I'm ready to write that out as 2 times s plus 1 divided by s plus 1 squared plus 4 plus now what do I need in my numerator over here to make this work? I need a b. Let me get a red. I need this b here, and so I need a 2 to appear in the numerator, but I only have 1, right? I only have 1 here, and so what I'll do is I'll put a 2 there and divide by a half, or multiply by a half. So now I'm ready to do the inversion using these table entries right here. Oops. I see that I have e to the what? Notice that that's s minus a, and that's e to the at, right? And so therefore the inverse Laplace is going to be 2 times e to the minus t cosine 2t plus 1/2 e to the minus t sine of 2t. Good. So this is my answer. Very good. Alright, so this is the trick now, is to sometimes we have to complete the square in the denominator. Good. Okay. Remember that the trick before that was partial fractions. So now sometimes we have to use partial fractions, sometimes we have to complete the square, just like in integration. So the last computation I wanted to make before we move into 6.2 is to write the following problem. Suppose that I define capital Y of S, to be the integral from 0 to infinity e to the minus st y of t dt, which of course is the Laplace transform of little y of t. Okay, what I want to do is I want to write, now write the Laplace transform of y prime. Let me even put a t here. I keep pushing the button on my stylus. Sorry about that. In terms of capital Y. Okay, so let's see what this Laplace transform of y prime is. If I write down the Laplace transform of y prime of t, that's the integral from 0 to infinity e to the minus st y prime of t dt. And now if I look at these two, I'd like to somehow convert y prime into y. How might I do that? Why, you can do that using integration by parts. So I'm going to use my table, plus, and now I've got an e to the minus st. I'll put it in the middle because I want to anti-differentiate my y prime, and then I'll have minus, the derivative here is minus s e to the minus st, and then the antiderivative of y prime is just y. And so what we see here is that my Laplace transform of y prime is equal to y of t e to the minus st from 0 to infinity plus s times the integral from 0 to infinity e to the minus st y of t dt. Okay, now when I look at this expression, as t goes to infinity, I need this expression to go to 0. Why? If this did not go to 0, I would run into trouble with the existence of the Laplace transform of y, right? And so I'm going to go ahead and assume that that limit is equal to 0, and then when I plug in 0 for t, I'm just going to have y of 0. So this is going to end up being 0 minus y of 0 plus s, and now this is the Laplace transform of little y of t, which is capital Y of s. So what we have just shown is something really important, so let me put it on its own line. The Laplace transform of y prime of t is equal to s times the Laplace transform of y, which is capital Y, minus y of 0. Good. Now let's keep going. I think we can do the next one in 1 minute or less. So how do I do the same kind of thing with the Laplace transform of y double prime? Why, I do exactly the same thing. E to the minus st y double prime of t dt, integration by parts, twice, plus e to the minus st y double prime minus s e to the minus st y prime plus s squared e to the minus st y, and so my derivative, or my integral I should say, becomes y prime e to the minus st, and then I say plus s e to the minus st y, and then plus s squared times the integral from 0 to infinity e to the minus st. I'm getting sloppy. I'm running out of time. St y of t dt. Good. Now these are evaluated from 0 to infinity, and so I will leave it to you to see if you can see that this becomes, oops, s squared times y of s minus s y of 0 minus y prime of 0. Okay, I'm going to leave that now, and we'll come back to it in just a few minutes.